Hi everyone, so Geoffrey Hinton released his recent research paper on dynamic routing between capsules, and when he released his work it's called groundbreaking, and today we are going to deep dive into capsule networks. So let's get started. Before jumping right into what capsule networks are and what they are really doing, we need to focus upon what convolutional neural networks are doing and what were the problems that we were facing with them. So just for a recap, CNNs are essentially a system where we stack a lot of neurons together over here, and these neurons have been exceptionally great at handling image classification problems. It would be hard to have a neural network map out all the pixels of an image since it's computationally expensive. So convolution is a method which strives for simplifying the computation to a great extent. So this is where convolution happens, and I've explained that earlier also. Convolution is basically a lot of matrix multiplication and summation of those results. After an image is fed to a network, over here, a set of kernels or figures scan it and perform the convolution operation. This leads to creation of feature maps inside the network. These features are then passed on to activation over here. For nonlinearity, these features are then processed by activation layers, for example rectified linear unit, to induce a sense of nonlinearity. Pooling helps in reducing the training time. It also gives you a bit of positional and translational invariance in object detection. At the end of the network, it will pass a classifier. So we repeat these fundamental blocks. We have a convolution block, then we use pooling layer, then we again use activation functions for nonlinearity, and this is just a simplified diagram of what convolution neural networks really are. If you go actually see the architecture, it's much more complex than this, and training happens based upon backpropagation of error matched against some labeled data. Nonlinearity also helps in solving the problem of vanishing gradients. So let's really deep dive into what each layer of convolution is really learning. CNNs understand an image at a more granular level, and if you're trying to classify pictures like cats or dogs, the innermost layer or first layer understands the small curves and edges of a picture. So this image right over here is an image which is trying to learn edges right over here, if you see. So this layer is learning the vertical edges, and this layer over here is learning the edges which are placed at an angle, which is making an angle to the perpendicular line. The second layer might understand the straight lines or the smaller shapes like curvature, and higher up layers start understanding more complex shapes like the fur or the textures of a cat or a dog. And final layers try to see a holistic picture like the overall face and the breed of a dog if we are classifying an image, let's say, of dog. But in essence, it also loses out the positional data. And here is a picture wherein we are retrieving images that are activating a neuron. So this visualization technique is of a large data set of images, and we feed them into a network and keep track of which images maximize activation of some neurons. We can then visualize the images to get an understanding of what neuron is looking for its receptive field. So what are the problems with convnets? First of all, they are translational invariant. So what does that mean? We are going to explain in a couple of minutes. Just bear with me. And if images are modified, let's say the orientation has been changed, whether the axis or let's say mirror image, then CNNs tend to show poor performance if they have not been trained upon that training set, and they are not a good way of representing human vision system. So we human beings have the most advanced vision system, and we gotta be taking examples from ourselves if we are gonna be improving neural networks for computer vision. And it has been put out in this research paper that convnets are still not a way of representing human vision system. and yes, they require tons of data for generalization purpose. And in my previous videos also, we have taken examples from ImageNet competition datasets, and they are trained upon millions of images before they can be deployed from some purpose. So let's deep dive into what are the problems which we are facing with ConvNets. So let's talk about translational invariance. So this image over here is right in the middle of a picture, and over here on the right is a picture of a dog located on the right hand side. And what does that even mean? Imagine that we had a model that predicts dogs. You can show it as a picture of dog and it's going to predict that it's a dog. But if the same image has been shifted to right, as in this case it's located in the right hand side, it still thinks that it's a dog without predicting any additional information. And this is what translational invariance is. That means when you show it a picture of dog located in the middle of an image and a picture of a dog located in the middle of right hand side of an image, it's simply going to predict that the dog is there in the picture. And ConvNets are unable to identify the position of an object relative to one another, and they can only identify if the object exists in a certain region or not. So if you were using binary classification, or so it's going to predict one in this case also and one in this case also, but there's actually a difference between these two images regarding the position of a dog, and this results in difficulty correctly identifying objects that hold spatial relationships between features. And what I mean by that, let's take an example of face labels. So for examples, a bunch of randomly assembled face parts will look like a face to ConvNets because all the key features are there. If capsule networks work, and they work as it has been proposed in the paper, they would be able to identify the spatial relationships between objects in the images, and they would be able to label it correctly. So this face has been divided into all these objects, and if we feed all these objects to the capsule network, it would be able to predict that all these objects are spatially related to each other and are, when composed together, will give a picture output of a face. Second example, they require tons of amount of data. So we have talked about transfer learning, and we have talked about pre-trained models like VGG16, VGG19, or GoogleNet for that matter. And all these networks have been trained upon huge amounts of data, and generating data can be a big problem if you are going to be deploying your model for some applications like self-driving for that matter. And let's talk about coordinate frame. The human vision system imposes coordinate frames on objects, and according to Geoffrey Hinton, when a visual stimulus is triggered, the brain has an inbuilt mechanism to route low-level visual data to parts of the brain where it can handle it best. So this image is the original image, and this letter has been inverted. And human vision, it's really easy for us to, tilt this image and do a mapping in our brain, and will still predict that it's letter C. Similarly N and R. And if we wanted to compare the object, we would do a mental rotation on the object to a point of reference where they are familiar before making the comparison. This is just not possible in convolutional neural networks due to nature of their design. And when a visual stimulus is triggered, the brain has an inbuilt mechanism. So we focus upon low-level features, and we then gradually build understanding of what these complex features really mean, and we take it to a level where it can handle best. And then we do reconstruction, and then we finally output an image. So let's focus upon inverse graphics network, and I'm telling you about this because it has been made use of in the original research paper. So what's really happening? It's the inverse of how a computer renders an object onto a screen. To go from mesh object onto pixels on a screen, it takes the pose of an whole object. This outputs the pose of an object's part in a lower dimension, which is 2 dimension in this case, which is what we see on our screens. like television. So why can't we do the opposite? Get pixels from a lower dimension multiplied by the inverse of the transformation matrix to get the pose of the whole object. Yes, we can. And by doing that, we would be able to represent a relationship between the object as a whole and the pose of the part as a matrix of weights. And these matrices of weights are view invariant, meaning that however much the pose of the part has changed, we can get back the pose of the whole using the same matrix of weights. So what is dynamic routing? Max pooling is very primitive way. So this is the original matrix which we have, and it has a filter size of 4 as you can see in this case, and a stride of 2. And the output which we are getting is 6. So it takes over the most dominant value, which is 6 in this case. So capsule networks is different as it tries to send the information to the capsule above that it is best at dealing with. So consider dynamic routing as a process of relaying information to another agent who can effectively process it, thus providing better efficiency. And we use iterative routing process. Each active capsule will choose a capsule in the layer. So there are nested neural layers. There are layers inside neural layers. And this iterative process will be solving the problem of assigning the parts to wholes. And this is just an excerpt from the paper, and we are going to read it out so that after watching this video you will be able to read the research paper on your own. And it makes use of reconstruction as a regularization method. So additional reconstruction loss has been used to encourage digit capsules to encode the information instantiation of parameters, and during training the activity vector of the digit capsule has been masked out, and this activity vector is then used to reconstruct the input image, and the output of the image is fed into a decoder. So if you are unfamiliar with what decoder does, bear with me, we are going to get back to it in just a couple of minutes. And then the minimization of square differences has been performed between the outputs of logistic units and the pixel intensities. And then the reconstruction loss has been scaled down by 0.0005 so that it does not dominate the margin loss during training. So let's get to what an encoder really is. The encoder tries to learn a function, let's say h of w, and it's a neural network which runs upon unsupervised learning algorithm, which then applies back propagation to set the target values to the equal to the inputs. That is, it outputs the output given an input. The identification function seems a particularly trivial function to be trying to learn, such as by limiting the number of hidden units, we can discover interesting structure that the data. So this image over here is a picture of an autoencoder, and it often ends up learning a low dimensional representation very similar to principal component analysis. This is the function which autoencoder maps. So let's get to an analogy of decoder with capsule networks. So a capsule network outputs a vector to represent the existence of an entity. So we have an original input over here, then we feed it to our encoder, and then there is a compressed representation, then it is again fed to the decoder, and then the reconstructed output is shown. The orientation of the vector represents the properties of the entity. The vector is sent to all possible parents in a neural network. For each possible parent, a capsule can find a prediction vector. Prediction vector is calculated based upon multiplying its own weight and a weight matrix. Whichever parent has the largest scalar prediction vector product increases the capsule bound. Max pooling routes based upon strongest feature detected in the lower layer. Apart from dynamic routing, which we discussed, CapsNet talks about the squashing to a capsule. Squashing is nonlinearity. So this over here, which we are going to get back in a couple of minutes, is a squashing function. So squashing is a nonlinearity. So instead of adding squashing to each layer, like how you do in convolutional neural networks, you add the squashing to a nested set of layers. These are the nested set of layers which you are talking. So the paper introduces a new squashing function for nonlinearity, and it squashes to 0 if it's a small vector and tries to limit the output vector to 1 if the vector is long. the dynamic routing at some extra computational cost. So capsule is a nested neural networks, and there are layers inside layers. So when the layer processes it, it's then again passed to the layers inside it. And neurons inside capsule capture the above properties of one inside an image. So here we are inputting an image, and then there's a nonlinear activation function which we are using, squashing function, and then it's being passed on to capsule, which is a nested neural network, and then it's connected to fully connected layers for that matter, and then this is L2 regularization, also called Fourier's norm, and then the output is generated. So it uses cosine of the angle between two pose vectors to measure the agreement for routing, and it uses the length of the pose to represent the probability that the entity represented by a capsule to present. And just for your thinking and what you can really do with capsule networks, let me just take an example over here. When you feed this image to a convolutional neural network, and there has been many research laid down regarding what the convolutional neural network is trying to learn from an image, and it seems that when this image is fed to a neural network, this is a picture of a man running in the place, and there have been several research papers carried regarding image captioning with convolutional neural networks, and it's really difficult for a convolutional neural network to predict whether the person is actually present in it and whether the person is running in it. So there's a difference in the state of the motion of the person. This person over here is running, and what traditional neural networks are going to do is they are just going to output a probability that the person is actually present in the picture. And capsules would be really good at different types of visual stimulus and encoding things like positions. If the image has been tilted or orientation has been changed, they would be translational invariant, and they would be susceptible to all these changes. And whether you change the orientation, velocity, or even the texture size, they would be really able to deal with all of that. So let's come down to the conclusion. So capsule network strives for translational equivariance instead of translational invariance, allowing it to generalize to greater degree from different viewpoints with less training data. To summarize, we are using reconstruction loss as a regularizer. The capsule network is able to learn a global linear manifold between a whole object and the pose of the object as a matrix of weights via unsupervised learning. As such, the translational invariance is encapsulated in the matrix of weights and not during neural activity, making a neural network translational equivariance. Therefore, we are in some sense performing a mental rotation and translation of the image when it's multiplied by the global linear manifold. And I think that it's a big game changer, and they are a significant improvements over what traditional convolutional neural networks is really capable of. And if we are really able to use transfer learning and like we normally do with convnets, and nowadays we are focusing on areas like zero shock learning rather than one shock learning, which is that we are relying upon less data and are making our neural networks more robust. So this is a significant improvement, and we'll be focusing upon implementation of capsule networks with TensorFlow, and there's more to come. And if you like this video, please hit the like button and please subscribe to the channel. Thank you for watching this video.